3D terrain maps. I think the technical setup is finished, right?
Yes.
Okay, great. Yeah, so thanks for coming. It's many more people than we actually thought. So thanks. And well, restart. So first, let us tell you a bit about us, who we are, who is talking to you. So this is Joy.
Hello.
And he wrote a diploma thesis, well, it's already written, he's handing it in as we speak, more or less, about avalanche risk visualization, and this is also what he will present later. And soon he will start a PhD with TU and FHAS.
Well, I mean, it's not fixed, but let's say TU for now. Yeah, I think that's good.
And he likes photography, and he's also in the TU space team. And we have some photographs of his. So we want to go super quickly through that.
Well, I don't know, like there's surprisingly few terrain or mountain photos in there, but still, I think it's just a nice overview of like some of them are from Vienna, some from the Alps. I think one or two you might recognize. The one was at the conference in Rome in the lower left, and then some wildlife from Africa as well. But yeah, I mean that's not what the presentation is about. So yeah.
Yes, let's continue. And a bit about me. I'm doing a PhD with TU Wien, and this whole terrain rendering is actually only a side project for me. And I partly do it because I'm so much into my mountains. That means climbing, ski touring, and also flying. And I also do bouldering. And so here you can also see two photos. The one on the left is from me flying, and if you look very closely, this is a paraglider, and there is a stone inside, which is not supposed to be. And on the right is from a ski tour where we also had to climb. All right. So this is what we will talk about. And if you have any questions, you can just interrupt and ask. So just feel free to speak up, to ask anything. There are no wrong questions, and if we get some sort of discussion, this would be very cool. I will be covering maybe something more on the technical part, so I will do some introduction to 3D rendering, what are tiles, how we load them, stream, cache them, and tiles are mostly 2.5D, so it's basically a height map. Then I'll also cover a bit of 3D rendering and vector rendering. So vector rendering for us means rendering something like Google Maps to the 3D world, which poses some extra challenges. And then Joey will speak about 3D visualization. So he will present his avalanche risk map, and he will also talk about terrain analysis and some blending overlay. And I think he has some very interesting things to talk about. All right, so let's start with a demo. And this demo is now also live. It's you can open it in your web browser, and there is also an Android app. It's an APK, not yet in the Google Store, and all of it is super alpha. So it's more of a tech demo than anything else. And here we have, this is Wilder Kaiser in Tirol. And one thing that you can see is the detail. It's not even the maximum detail, but you can see single trees in it. And here we have a path, and I think, maybe a bit. You can also see that the terrain depends on the path, and in the full resolution version this is visible even better. This is when we zoom out. And here we also have some labels, but these are hard-coded right now. Yeah, and you can see some rock formations. to a more important mountain, which should be here. Somewhere. No? Okay, never mind. You've seen this thing. Let's go back to the presentation. All right. So the first thing is what are actually map tiles, and for that I have this overview. So this is not from us, but it shows it really well. And basically, map tiles are a quad tree of the whole world. So we have the root tile at the very top, and in each level we divide each tile into 4 pieces. And this is not loading. This is perfect. It should load. Why isn't it loading? This is also not loading.
Yeah, maybe the internet stopped working.
Let's try with the hotspot. Now we have it. So here we see the root tile, and there are 2 different tile IDs. The one is in the Google system, the other is in the TMS system, and we are on zoom level 1. So when we zoom in, we divide it. And you can see that every tile is counted with the Google system. For instance, top left is 0, 0, we have 1, 0, 2, 0, etc. down until 3.3. And the more you zoom in, the larger the numbers here become. And from this one, we can get a tile ID. So the tile ID would be, for instance, the zoom level slash the y coordinates or the x coordinates slash the other coordinate. So this is how we can identify each tile and uniquely for the whole world. So when you zoom in to Vienna, for instance, we have zoom level 14 and some numbers here. And so these are tile IDs. They work like here for vector data. Actually, it's rasterized vector data in this case, but it can also be orthophotos, or it can also be height data. And what we need in this 3D renderer, it's the color data, so that's something like this, and we also need the height data. And height data, it's a floating point value, for instance, 3,201 meters above sea level, and these are images, and the images, that each channel has only 8 bits, so it's 1 to 256. So we need to do something special in order to encode these things. because we want to send the data using normal images, because on the client it's easy to unpack a normal image. If we had some special kind of TIFF images, the browser would have, for instance, problems unpacking that. And so what we do, and what is widely used in the industry, is to simply convert the float to an int. So that's 32 bits, or it can also be a shorter int, like 16 bits. And then we cast this int simply to a color. So in here, you can see what this results in. You have these waves, and on each border of the wave, one of the colors, so the green, it's red, green, blue. So I think the blue is the less significant, and the green is the more significant. So the green changes from 0 to 255 very quickly, and then on the border, when the green is full, the blue switches one bit further, one number up. So that's how we encode images, and in this case, I think it's a 24-bit encoding. So we have height with a 24-bit encoding. Alright, so now that we have the image data, the texture, and the height at the client, we still need to generate the geometry and then draw it. So the geometry is drawn simply by creating a grid and displacing each point in this grid according to the height map. This is super simple, it works, it's nice, and we can render it. Only that there can be some issues. And the thing is, if we stay within one zoom level, then everything is fine. However, when we have the border between two different zoom levels, then cracks can be created, because the lower zoom level is less precise in the border. And so the higher zoom level, it can be, for instance, down and up, while the lower zoom level just goes flat. And so we can get such cracks. And there are several solutions to them, none of which is implemented currently in our renderer. But the simplest solution is actually curtains. So simply, if you have the tile, at the very end of the tile, it just goes down, say, 100 meters or something. So since it's all 2.5D, this would hide any cracks. But it's not very nice, it's not a clean solution. And you can also manually shift around in the higher resolution tile. You can shift around the vertices so that it matches up with the lower resolution tile. However, that means that we would have to change each tile before drawing, depending on the neighbor. So that's a bit finicky. But there are some relatively elaborate algorithms that make this possible and that make this easier. One of them is raster by Bush et al. And what they do is they use, instead of rectangular grid patches, they use such triangular patches, like you can see in the lower left corner. And here we see examples like they can also change resolution. The higher resolution our height data is, the more resolution we can put here. And what this gives us, you can see on the right, we can, of two different levels, we can align the longer edge with the shorter edge. And if we do this, it's guaranteed that there are no cracks, because both tiles are in the same resolution. So what remains is that we have to set up a system, an algorithm that creates us a field of such patches in such a way that this condition is met. So we can maximally switch between two levels. We can switch more levels, and it needs to have a certain layout. but then it works and it's crack-free geometry. Alright, so these are the very basics, and this is basically how the render works. But there are several problems with that. First, like we know that we need to load and unpack data. We know how this works, more or less. We know that we will use a grid mesh, displace the height fields, etc. We know how to render it. But we still don't really know which tiles to load. Like imagine you have a camera somewhere flying over Austria or Slovakia, and you need to know which tiles to load, which tiles to display. And sorry, but this will be a bit of a wall of text, but we didn't have time to do nice images. So first, let me explain what we do in order to find out which tiles to load, and then I'll also talk a bit about caching, which is very important as well. So the first thing, you saw that these tiles have IDs, and that for each ID the tile is placed somewhere in the world. So if it is placed somewhere in the world, it's possible to get from this tile ID to bounds. So for now this is only the X and Y bounds, so we know where it is. What we did as well is go through our data in a pre-processing step, and for each tile store the minimum and the maximum height. And this information we deliver to the client, and together with the binary, let's say, together at the beginning. And so this allows us to tell for each tile to make an axis-aligned bounding box. So that's what we have now. Then we can cull this axis-aligned bounding box with the camera frustum. So this means that all tiles that are away from this frustum fall away. Then what we can do is search for the closest point to the camera from this axis-aligned bounding box, transform it using the camera matrix, and now we can tell how large this point, this closest point of this tile, looks in the screen space. And with each tile we have an associated texture, so this is either this height map or the color map. And so if we know a lower bound on how large this texture is in screen space, then we can decide, yes, do we need more detail in this tile, or is it enough? So if it's enough detail, let's say if the texture is more or less in the pixel size, then this is the right tile for us. So we can compute how large a pixel of the texture would be in screen space. We want it to be about the size of a pixel in the screen. So the texture should be about the size of a pixel, and then we are at the right tile. So this tells us whether we should load this tile, but it doesn't completely solve the problem, because we can't simply go through all tiles. For instance, for a zoom level of 18, which is entirely realistic for us to display, we have, I think that's 68 billion tiles in the world. We can't iterate through all of them. So what we do is to go through the quad tree of the tiling system, and in each node we do this test, and we check whether this node is already detailed enough. If it is, we are good. If it's not, then we descend in this node. And with this algorithm, we can generate a list of required tiles for an arbitrary camera position. And other systems, they do something much simpler. They look, for instance, at the position of the camera. They calculate the distance to the tile center, and they decide based on this distance whether they load it or not. And this you can also see sometimes when you look at renderers. I think Matt usually does it this way. Yeah. So now we know which tiles to load, but especially here, you know that internet bandwidth is not infinite. There is delay, and frankly, the server will also be sad, and our server was sad very often if you simply request too many tiles. So basically, it was not our server, it was the server from the city of Vienna, and it simply blocked us. This means several things. First, since we can't load everything at once, we will load lower zoom levels first so that we can displace something more quickly. Then we have relatively aggressive caching, and in fact, I would say that our caching is more aggressive and nicer than, for instance, Google Earth. And then we also have a rate limit. So if we request too much, there will be an automatic throttling. So let's talk a bit about caching. The most classical cache is an age-based or a frequency-based cache. So this is what the web browser uses most of the time. However, we said that if we have no higher resolution tiles, we want to show lower resolution tiles. However, most of the times we will see these higher resolution tiles. And this means that the lower resolution tiles will not be requested. And this again means that they will fall out of the cache. So this is something that we can't really have. Another problem, but this might be only our implementation, you relatively quickly arrive at that you want to cache 100,000 tiles. That's our current limit, and our caching system had problems with file descriptors and stuff, and it simply after some time it stopped working. I don't know, maybe there was a memory leak or something, but 100,000 files is also not exactly good for the file system. You talk a lot to the operating system which files you want to write. It's simply not optimal, and all of these files are something like 16, 20 kilobytes of size. So this is simply not optimal. Another thing, like I described before, this algorithm that we go from the root to the children. And so what we actually do is when we render, we also go from the root to the children. We check whether this tile is in the cache, like we have several levels of cache. So for instance, we also check the GPU cache. If it's on the GPU, we can issue this draw call. If it's not there, we stop. And so this means if we kick out a certain node from the cache, then we can't descend to the children, even if we have the data. We don't see it.
I have a question.
Yes.
Can you just create a placeholder for the kick out mesh so you could still reach the children?
So the question was whether we can put a placeholder mesh for the kicked out tile.
Let's say just some pointer that in order so we could still reach the children, so you don't have to kick them out.
Yes, this is technically possible, but it makes the whole algorithm even more complicated. It's also possible to, if we are missing a certain tile, what we do is we store the tiles in the quad as quads, and if one of the tiles is missing, then we consider this whole quad as not complete, and we will not draw it in order not to have holes in it. And it would also be, in this case, it would be possible to replace it with the lower resolution data that is one level up. However, this brings a lot of problems. Like, say you did this over several levels, and then one of the root tiles arrives, and then you would have to replace several levels of data. All of that is possible, but it makes this whole thing more and more complicated. And so, yes, at some point, probably we will implement something like this, but for now, it's just too complicated. Right. So I already teased it. We store the tiles in a tree. We store them as quads. So if the quad is not complete, we consider this node as incomplete. Then we have a visit function with the camera, which always goes from the top to the bottom. When it visits this tile, it updates a timestamp. And this is done in such a way that the tiles in the lower zoom levels, so up the tree, they will get this timestamp on their way back. So they will always have a newer timestamp as the children. And then we simply can evict the tiles based on age. So this also means that tiles that are highly detailed but far away from our current camera view, they will not be visited, and so they will fall out of the cache more quickly. Oh, and we store all of the tiles in one single file, so this also solves the problems with file descriptors, etc. Okay, so all of that was 2.5D, and from now on, I'll explain parts that is more like ideas of ours. We think that this is the way to go, but we don't know yet. From now on, nothing is implemented. So first, why do you want to go from 2.5D to 3D? And I hope this is visible. This, I think, is the Dutch style, and it contains a very steep, it's vertical, a high vertical wall. And since all our data is like a texture on the horizontal plane, we don't have any detail for vertical stuff. Even worse, if there were some cavities, some hangovers, or something like this, there wouldn't be even a way to represent that. And so that's why we want to go to 3D. Because if we have 3D, we can have triangles in 3D, we can have normal unwrapped textures in 3D, and it won't be so easy to store them because we can't use the same tiling scheme and the same tile IDs. But like for the data representation, it can be much richer. And so before we had this level of detail based on the texture size. Now that we have geometry, we would need geometry simplification, or mesh simplification. So here you can see on the very left a highly detailed, and on the right it's the lowest detail. There are a lot of mesh simplification algorithms, so we are not covering them. But also if we simplify meshes, we will have the same problem as with the tiles. So the simplest solution for the cracks in the tiles in the 2.5D based system is to simply make curtains. This works. But if we have meshes, it's not that easy anymore, because in which direction do the curtains go? They can't simply go vertically down, because there can be some other parts of the mesh.
One question.
Yes.
Did you consider using GPU tessellation to solve these connectivity issues, where basically all the tiles would be the same resolution, and then you would use like tessellation shaders to add more detail, which is guaranteed to connect along the edges?
So the question was whether we were considering using GPU tessellation. No, for two reasons. First reason was that we are using WebGL2 for now. So there is nothing about that. But even if we used Vulkan or WebGPU, which is probably something that we want to do in the future, even then, I mean, yes, then you could move around these things probably more easily. But still, from the setup, from the algorithmic part, I think it's much more complicated than what we do now. Like right now, we are simply generating a grid. We can add the curtains. We are doing that, and in fact, we are on CPU side. We are not storing any geometry to the GPU. We are just sending the indices and the heights. And the GPU computes the position of the vertices. It would work probably, but it would be more complicated. Even more so in the 3D part.
Yeah.
And also, like, remember that the tiles, the geometry, is loaded from the server. So the whole geometry, like the height data for all of Austria, it's about 1 terabyte in size. The color data is another 2 to 3 terabytes, most likely. So there is just no way you could send that to the client, or even store it at the client. Right, so we also have this problem with cracks in 3D, and it's not so easily solvable with cartons or other algorithmic things because we have many more dimensions, or like one more dimension. So we took we looked at Unreal's Nanite. There is a link, everything blue is linked. I think the slides will be available. And this is from the SIGGRAPH presentation. So Nanite tries to solve some of the problems that we have, but they have a lot of other problems as well. And like our setting is different. So what Nanite tries to do is to have triangles which are about the size of a pixel. But they don't have internet streaming, they're streaming only from the hard disk, or even not that, like everything is on the GPU. And then it's only about selecting what they render so that they have enough budget. Also, they expect relatively big GPUs with compute, etc. We actually want to render on the mobile phone, and we have a mobile phone app. So these are quite like different. How do you call them? Different circumstances. Yes. And we are drawing fewer triangles, so we don't care if one triangle is, I don't know, 100 pixels in size. That's fine for us. But still, they have a very interesting LOD strategy, and this is what we kind of want to see. So one possibility to prevent cracks would be to not simplify the borders or the edges of the patches. So back in tiled world, we could simply say, like right now that we have meshes, we could say that on every tile border we keep the original resolution. Some levels this would work fine, but if you imagine you're to a very low zoom level, and on the border of this tile you still have as many vertices as in the highest zoom level. So here is also a picture of how this would look like with a mesh, and very soon also you can't simplify inside the patch. Yes, so there can be some dense craft along the edges. So this is not what can be used. And this is also visualized by like this tree. So this is like a quad tree and in the middle, like when you can draw this line from the root node to the bottom, in that case, there is such graph. So what they do is that they group triangles into clusters. Within each cluster, they again run the simplification, and the clusters change borders between levels. So you still have this thing. So if you actually they change borders every second level. So if you go from one level to the next, you have the same border, and this border is then fixed like before, but you simplify within. And then for the next level, you change the border again and you fix a new border. There was a question? No? Okay. And this is how this looks like. So this is, let's say, the highest level zoom. Then you simplify within these patches, and you find new borders. So this is an example of borders for the next level. And these go along, like in each of these polygons. Each of them is actually a patch of many triangles. Let's say it can be 100 triangles or something like this. Just some examples. So you can find edges within that, so that you create larger patches for the next level. And you go on. So again, you selected new patches, you simplify within, and for the next level, you again find new borders, and then you simplify within. And this way, like along these green edges, you have these are edges between vertices in two different levels. So if you want to have the red zoom level on one part, you just have the red zoom level until a green border, and then you start with the green zoom level. And this is like about the same thing, but a bit in a bit more detail. So how to create a next zoom level. So in the higher zoom level, you pick n clusters, a group of n clusters. So each cluster is such a triangle pad, and you pick a group of them which are connected. Once you have selected them, you merge all of them, and then you simplify within this group. Once this group is simplified, you split it up again in half the number of clusters. So at the beginning you have 4, at the end you have 2 clusters. And these 2 clusters are then of a lower zoom level. So they have a rougher geometry. As you can observe, the border of this patch is the same. Okay. And what this forms is on the lower side of the screen, lower right, you can see that 2 new patches each connect to 4 patches in the higher zoom level. So instead of a tree, we now have a directed acyclic graph. And now when you go from the root and you make a line down, you see that it crosses edges in the DAG. And as soon as you have the situation that you cross edges in the DAG, then you don't have this problem with accumulating craft at the edges of the patches. All right. And so the next thing is, right now that we have this DAG, we have the patches. We need a way to select what to draw. And especially for nanite, it would be problematic if you would have to look at this whole thing to make this decision, because they are making this decision in a compute shader and they don't want to have dependencies. So what they realized is that these decisions are completely deterministic. So you can do them in parallel for the lower and the higher zoom level. And if you do the same decision always, then you're good. And you don't need no synchronization between the GPU threads. Or in our case, we can do the same decision in the drawing function, which might also be on the GPU, and also in the function in the thread, which is in our case it's a separate thread that requests the tiles. In that thread we can have the same decision and they are completely independent. And so the core here is that all clusters in the group must make the same LOD decision, and in that case, you're good. And this is another view of this. Like, imagine that you have this tree. In this case, it's a tree, but it would be the same thing with this DAG. What you're trying to do is make a graph cut. A graph cut, and above this graph cut, the level of detail is too low, and under the cut, the level of detail is too high. And so you want to display right the border of this graph cut. All right. That's it for the geometry part, and now I'll have some more about vector rendering, and I'll try to hurry up a bit. Vector rendering is basically what Google Maps does in 2D. However, in 3D it's a bit more complicated because of quality issues. And there are several options. You can draw into texture, very much like an orthophoto texture, and then you can simply render it. You can create 3D polygons above the surface, so that, for instance, a path is actual geometry, or you can render this whole thing in screen space. So let's go through these options. Here is an example of mapping.cz. I just found out about it yesterday, and I think it's a very good example of the first method. So you're a bit far from the screen, so you will not see it. But here in the lower left, where the texture is very close to the camera, you can see the pixeling and the filtering that is going on in order to increase the zoom size. So the problem here is that the texels are too large for the screen pixels. While over here in the background, there are some aliasing artifacts. All of that is getting more complicated because, for instance, here on the slope, the texture, like I showed you before, it's still 2.5D. So the texture is stretched, and you again have aliasing artifacts. The next example is creating polygons. In this case, the example is from fatmap.com, and there can be several issues. One of the issues can be that you have Z fighting. The other issue, I believe, I'm not completely sure, is that I think this will be just slow. You have, for every polygon, you have to look up the heights. And the heights depend on the current zoom levels. So if you load in different zoom levels, you have different heights, and you need texture lookups and everything, and you simply have a lot of geometry. So, and there are also some problems. Somewhere I saw them. Yes, like over there or over here, it's not connected. So this is another problem. The third option is to do screen space rendering. So basically, this works in this way that you store the whole vector data in a huge spatial acceleration structure. And then when you render them, it can be, for instance, in the fragment shader, or it can be in a deferred rendering pass. For each pixel, you compute the position in world space. Then you query this acceleration structure, which geometry is nearby, which vectors are nearby, and then you decide for the color of this pixel. So this is instead of drawing a line from this to this and walking the pixels, this would say, okay, I'm here. How far is the line? If it's so close that I'm inside the line, then I'm coloring my pixel. And I would say that this gives the highest visual quality, but it's also not super fast. Ami Rakdam, whom I visited in Switzerland, he made a paper, I think it was 2020 or something. They rendered the whole network of streets or lakes in Switzerland, and they got around 30 frames per second on a GeForce 1080, which is more or less okay. But if you want to go to mobile phones, etc., this is just not going to fly. Alright, so we have texture-based, which gives us aliasing artifacts and problems with the level of detail. We have polygon object-based, which we think is expensive, and it also causes set fighting. And then we have screen space, which is the highest quality, but also expensive. And our idea for that is, very roughly, to use texture rendering. However, instead of doing this in this UV space, which is basically the world coordinates, so in this vertical projection, we can do simply some UV unwrapping, and this UV unwrapping can be even optimized for the vector data that we want to show. So for instance, we can give more texture space where we have a road, and where we don't have anything, we can compress this texture space. So this basically means that we are using this texture space more efficiently. And also, instead of rendering color, we want to render some intermediate data, so some intermediate information. So for instance, this could be a distance to the path. And then when we when we read the texture, we can read several pixels, and from that we can compute a more accurate distance for the current pixel on the screen. And this means that we hopefully can compute a more precise color with less artifacts. And so basically this would be then rendering to texture and then finalizing in the fragment shader or in a deferred class. And what we could also do is render into several layers and then land. For instance, roads that are too far away and not important enough, they should simply go away. Alright. And I think that is it for me.
Okay, so let's switch over. Okay, so welcome also from my side. Adam talked a lot about the very detailed technical backgrounds of the terrain rendering itself, and I'm focusing a bit more on some visualization techniques on how to actually transport additional information beyond what's the terrain model itself onto the terrain model and in some visual representation. So what I did, as Adam told in the beginning, I recently finished my diploma thesis where I did avalanche risk visualization, and that's also how I joined this whole project basically, where the idea is when you go out skiing, you want to have an idea of what the situation is out there. And I mean, this is only a Photoshop mock-up of a photo of me and the map projected like photoshopped into it. But the idea is that you have a 3D representation of mountains, which is very detailed so that you can match it up with the real world situation, and thereby can also then recognize potentially dangerous areas. And what that looks like is, maybe I can actually give a live demo. I hope this works with the internet connection. Of course, the link is behind the video. That's great. But here I have a browser. There's a screen this. And I also have the same data set as Adam was using for Austria.
Microphone.
I have the same data set, but I'm using a different renderer because back when I started with the project, Adam was also still just starting with the development of the Alpine Maps renderer. And so I'm using MapLibre, which is a different rendering framework. Thank you for, let's refresh that one. Didn't like this change in screen size. Yeah, so I have this same 3D terrain model. As you can see, it is not the best. It looks a bit different because we also have some vector labels in here, which use this render to texture approach, except for the text, which is rendered onto billboards. And what I can do here is I can add different overlays. So for example, I can look at the overall avalanche danger ratings. So for those, there are different danger levels. Basically, it's similar to a weather report where there is an authority who says you take measurements on different slopes and then get an overall avalanche danger level. And what I can do here is I can display that on the terrain model, and basically just have like a color overlay on the terrain, and can see, okay, different parts of Austria have different avalanche danger ratings. And so for example here in the orange part we have a 3, so it's probably rather dangerous, but it doesn't give very high resolution information, so to say, because basically it's for bigger regions. So what I did, I combined that with analyzing the terrain data itself, so that I can actually see for individual slopes, once the data actually loads, so that I can see for individual slopes how the situation is, and have a more detailed way to look at the avalanche danger or the avalanche risk in this case, because it actually combines the static terrain information with the dynamic avalanche risk as it's reported by the authorities there. And I have a few different such overlays. So I also have, for example, a static overlay which just computes the slope angle, so that always stays the same, of course, except that there's a landslide or something, then you need your data. And there is also like a simplified risk overlay which just displays areas which are especially dangerous in red, so that you see more of the underlying terrain underneath it. And like as an additional feature, I also have a terrain inspector tool where I can go into an area then and see, what the actual situation is on this point. So I'm in a 3 here. It's a rather steep slope of 42 degrees, so it's not a big surprise that it's in a deeply red area. And the basic idea of this whole thing is to help backcountry skiers who go on ski tours to plan their tours and be more aware of potential risks along this tour. Yeah, so that was a little overview. And for the rest of my presentation, I'm now going to talk a little bit about how I did this terrain analysis and what are general rules for building visualizations onto a 3D or 2.5D terrain. So basically what I start out with is the terrain model. As Adam described, it works very similar to his renderer, where we just have a height map in this color encoding, and it displays as a grid mesh. And then I also put on an orthophoto so that I have a textured terrain mesh. And the first thing I derive from that is the slope map. where basically I just take the derivatives of this mesh, although I actually don't take the derivatives of the mesh. I'll go into that a bit later, because I don't actually need the mesh information. And in addition, that's just a technical part for these avalanche danger ratings, because they come in different regions. And I want to do the whole computation on the GPU. So I also have an additional texture input where I have the regions encoded in color, so that I can look up for each pixel on the terrain what the region would be. And of course, from the height model, I can also have different heights, because as we've seen, there have been different danger ratings for different heights in the avalanche report. And I can also, of course, extract that information from the terrain model. And with that, I can arrive at this avalanche danger rating overlay. And for the actual risk visualizations, there are different methods that recreationists use to determine the avalanche risk based on terrain features as well as the avalanche danger rating. And one of them is called stop or go. That was the one where the red overlays were. And for that, basically, it's just a combination of having the slope steepness and the avalanche danger rating. And based on that, I arrive at a risk rating, which tells me these slopes are a stop or these slopes are a go. And then there is also this other risk rating, the one I showed at the very beginning, where it is called the snow card. And here there's additional information that's added, which is the exposition of the slope. So whether the slope is facing to the north, to the south. And that can also have an influence on the avalanche risk, because, for example, the sun or the wind is a directional influence on the slope, and therefore it can also influence the avalanche risk. And here I have a bit more complicated encoding, so to say, because we actually have different risk levels ranging from very low risk for the bright white parts through the yellow and orange to the dark red, where it's a very high risk. So that was a little overview. Yeah, I built an application using MapLibre, where basically I have different tile sets. For example, one of them is the digital elevation model. One of them is also a tile set for the regions. And then, of course, also the real-time information from the avalanche report. And the visualization part really happens in the renderer then at the end, where all these different tile textures are combined, and the risk level is finally computed on the GPU, which also allows me to have real-time updates basically, and I don't have to pre-compute these risk tiles and build the whole tile, the whole quad tree for the tiles, but I can just compute them on demand whenever I need it. So there's also something more fundamental still, which is quite important for what I'm doing. For a terrain model, we have this height information, which is, for example, stored in tiles. But there's different types of this information. There is digital terrain models, and there's digital surface models. In general, they are like the overarching term would be digital elevation models. And the digital terrain model basically just displays the terrain. So in the figure here, you can see the terrain model would be just the ground floor, so to say. So it's just the black line here at the bottom, where all the additional features such as trees or buildings and so on are not part of the model itself. Whereas the surface model just represents the actual surface that is with trees and roofs of buildings and everything. And the cool thing is, the way this data is captured is usually by LiDAR scan. So you have a plane or a drone flying, and you have a LiDAR scanner where you send down these infrared laser pulses, and then based on the reflections of them, you can measure the height. And the thing is, once you send such a pulse, it's actually not like a laser pointer where it's just an infinitely small point, but it's a bit of a larger area once it reaches the ground. And so if there is, for example, a tree in the way, it hits the tree surface, the canopy of the tree, and gets a reflection already back, because the leaves, of course, reflect that LiDAR scan. But not all of it gets reflected, some of it just goes through and continues all the way to the ground. And so you get a second reflection. That's how you can basically get both of these models for free with one single scan. And I think that's pretty cool, and for me it's really useful, because avalanches usually, there are avalanches on trees when snow is just falling down from a tree, but that's not usually the dangerous thing you're looking out for. but you're actually looking out for avalanches that have huge masses of snow moving on the ground. And so I used the digital terrain model for calculating the slope steepness, which is one of the main inputs to calculate the avalanche risk. And I still also use the digital surface model because I want this very high resolution representation of the terrain, where you can see landmarks such as trees or individual huts or whatever that can help me navigate in the terrain. And so I'm using the digital surface model for rendering, but the digital terrain model for the terrain analysis. And when I talk about terrain analysis, one of the things I do is I just looked at cartography and what they're doing, because they're actually really smart about visualizing maps, because I mean that's basically another name for cartography, right? And they have a technique called hill shading, which is not necessarily a technique for 3D terrain rendering, but just a way to convey the steepness or the 3D topology of the terrain on a map. So if you look at a map like this, it actually has all the information in there. That's what I'm telling you now. I mean, you can't really check it, but it's actually a 3D map. There's just no shading applied to it. And you have the roads in there, you have information about the ground cover and everything, but you can't really do much from it because this is missing. And hill shading is a way to obtain this gradient information, and you don't actually need to apply any proper shading as you would when you're rendering the mesh, but you can just obtain these gradients from the height data itself. And for that you basically, okay, here's the same again, for that you basically do a sampling of the mesh, of the terrain pixels, where I'm just looking at the elevations that are the C values here, and I want for the point C00, I want the gradient. So I just basically do the partial derivatives for this pixel patch in both directions, in the x and in the y direction. And from that I arrive at the derivative then, and from that I can of course really simply obtain the slope angle and additionally also the aspect angle. And the aspect angle is just another name for the exposition basically, where I have the different orientations of the slope. And the cool thing about this is I don't need a mesh for that. I can just read the pixels and take the elevation values from the pixels to arrive at these derivatives. So I can use the digital surface model to build my mesh and render it, but I can analyze the digital terrain model underneath, and I don't actually need to build two meshes to do that. So yeah, that was basically the only terrain analysis technique that was needed for the avalanche visualization. And in summary, like what I did for my thesis there was I took all different information sources which people normally use for their ski tour planning. So that would be like this avalanche report, which is normally just published as a PDF or as a website where people can read up on the information. And then I took terrain information such as the slope steepness, which of course also is available individually in some maps. And then I combined it with these risk evaluation methods, which also existed before, so I was not inventing new methods to calculate avalanche risk, because I'm not actually an expert in that. But what I did is I combined all this into a single visualization, which can hopefully help recreationists to do more in-depth risk analysis for their tours, and to also help them to do, to just have less work to do when they want to evaluate the risk. Of course, what also has to be said here, it's not all. People also still need to check the actual risk on site and decide based on that. That's just an important disclaimer. So I also have a demo application. It's on the university server at the moment. You can check it out if you want. I think the links should be published in the slides then anyway afterwards. It was the same one that I showed you before, and the cool thing is it also works on the phone as well. So you can actually also use it in the field if you want to go on a ski tour and check out the risk. That's also possible. And so for the last part of my presentation, I want to talk a little bit about more general visualization challenges for 2.5D or 3D maps. And here the thing is, for normal maps, there are quite some difference between like normal 2D maps and 2.5 or 3D maps. And one of the big differences, Adam also touched upon this a little bit, was that with a 2.5D map you don't have a constant map scale, because you can tilt the camera, and as soon as you tilt the camera, parts of the map that are further in the background actually have a different scale. There is perspective involved, and as soon as that is the case, you have a compression of the information in the back, so you need to somehow handle this not only for vector rendering of roads and such, but also if you want to visualize something on the map. Of course, then you also have occlusion. Something is behind the mountain that can happen in 3D, that can't happen in a 2D map. And yeah, the limited visual budget and visual clutter kind of come together. You can only do so much information on top of the terrain, which is also already high frequency information, because you have trees in there, you have mountains, you have the aerial images, for example, and all of this is already a lot of visual information. And then putting something on top of that even can lead to some challenges. So here I just have like a little overview of what you can do and where you can put the emphasis. So you can either have a very simple overlay where you focus more on the underlying terrain model and just have some colors on top. That's basically what I did for the avalanche risk visualization, because I really wanted to have the underlying terrain in combination with the avalanche risk. But then of course you can also say, I want to focus more on the risk encoding itself, and have that one and just the terrain as a suggestion underneath it, which conveys a different kind of information. You put the focus somewhere else. And the third you can see here is actually this. That's an example I took from a paper where they had 3 different information channels, so to say. One was the terrain itself, then one was a risk level, and the third one was the uncertainty of that risk level. And here in the third picture you can see that they encoded the uncertainty then with some glyphs overlaid on top of the risk level. And you can see if you the more information you put into this visualization, the more cluttered it gets, of course. So yeah, as I already said, I more or less took a very simple approach to the visualization, because I took overlays, and of course they come, for example, with the problem that they occlude the base map. And for my visualization, I tried to overcome this by just having the ability to switch between different layers, so that I can turn on and off the different risk levels or the avalanche danger rating, and just see the underlying terrain underneath anyway. And yeah, it's maybe not optimal, but it's also a really hard problem with different trade-offs here. If you want to do blending, there is a really nice website from the cartography people, once again, where they looked at color maps that work well for blending with, in this case, actually 2D maps, but you can also at least have a shaded relief terrain as a base map here. And that's also where I took my color encodings from for the map, because it's a really nice resource, and they actually tested it. You can filter for example, color maps that are compatible with different kinds of color blindness, or compatible also with different kinds of data, like not only the sequential ones, but also diverging color maps, and also qualitative color maps. So if you ever do a visualization on any map visualization, or actually any visualization, I used this website before I even worked with maps, because it's just a really nice resource for color maps. So that's a recommendation here. And finally, like for example, what's also been done in a scientific setting, not so much in the publicly published maps, is, for example, encoding overlays in different parts of the color information, so that actually it's the hue and the saturation, or also the lightness, the value, encode different parts of the information in the map. They have volcanic maps here where they show differences, for example, in how the lava distributed over different years, and then they used different channels of the same of the overlay to actually arrive at these visualizations, so that there's higher information density in there, but it also kind of makes it harder to read the map, and it only really works if you have a grayscale base map underneath it. And another technique, it was already shown in the overview a little bit, would be to add glyphs to a map. But that also goes only so far. So you can do it to emphasize specific information on some localized points. But for example, glyphs won't really work well for avalanche risk visualization because it's more area based. And just adding glyphs for all the different potential areas where there is avalanche or elevated avalanche risk could lead to some visual clutter really fast. So you have to be careful with how you apply glyphs onto a terrain map, which is already usually quite dense from the visual clutter. And then one idea which I didn't actually implement, but which I really want to implement in the future for the avalanche risk visualization, is this hashuring or hatching. It's called. It's basically based on the way hand-drawn maps were representing terrain steepness and terrain shapes on, of course, 2D maps because they were hand-drawn. They were just paper maps. And there you can see different ways of representing the terrain features. So one thing is these contour lines. I think most of you probably know them, like these lines of equal elevation. And in addition to that, there's also these little hatches here, which basically show the slope direction and a bit of the shape of the mountain. And you can of course also do that on a terrain model. And the idea here, or my idea here, is to use these lines also to encode additional properties. So this is from related work where they use the Hashure lines to encode, for example, the aspect also. So you can see all the slopes facing in our direction here are encoded darker, whereas the ones facing in the other direction are encoded lighter. Or for example, the steepness also in the other image here, where the steeper slopes have either more dense lines or also darker lines. So there's a couple of parameters that you can use to encode additional data here. And how you arrive at these lines is basically you just can take the normal contour lines and then draw just normal to them your curves for the hashures. And then you can have different encodings, so you can have different thicknesses, you can have different shapes, different lengths. And with all these parameters, you could encode additional information. And the cool thing is, avalanches usually follow the flow of the slope, because they rarely ever go uphill. So I could actually also use that to get an idea about the avalanche paths in the visualization. Because right now I only have basically the risk in areas where where there's an elevated risk of triggering an avalanche. But it would also be interesting to see if there is such an area above me, where does the influence actually go? And I believe that using something like this in the visualization could be really helpful here. So yeah, here's just some more examples of how you can have the same terrain model, so that all has the same underlying data, and use different line properties here to encode different information or just to emphasize various parts of the terrain here. And of course, it doesn't have to be black and white. You can also combine it with color information. Here, for example, we have the two channels that I used in my terrain analysis, which is the aspect angle and the slope angle. And there's just like a color encoding for the aspect, and then line properties like thickness and line length encodes the slope angle. I think in this case again, it's 2D, but if I map it onto the 3D terrain, I can also use different channels. Of course, I can have the slope and the aspect already visible in the terrain, and then use the avalanche risk as an additional channel, which I encode these lines. So yeah, that was a little overview on visualization techniques. And to summarize, basically, what can you take away from this? There is no general solution for just saying, okay, this is the best way to do visualization on 3D terrains, because it's always very dependent on the context, what you want to show. If it's very low density information that's localized, then maybe the glyphs are the right thing to do it. If it's more area-based, the overlay could be the way to go. And yeah. Basically, what I learned from my project is look at what cartographers do. They are the experts in map making, and we can maybe then implement their techniques more efficiently on the GPU or something, which is basically what I try to do for my diploma thesis. But a lot of information, a lot of research is actually already out there. It's just like usually not in the field of visualization and more in the field of cartography. So it actually pays off to look into what they're doing there. And one question I think that's also okay to be asked here is 3D even necessary? Because it's super nice, for example, for the outdoor activities in the mountains to have the ability to view the map in 3D, but a lot of times it might actually be sufficient to have a 2D map. So that's also one thing you should think of. You shouldn't just go to 3D for the sake of 3D, because it's cool and you can use all your computer graphics knowledge there, but maybe sometimes it's actually also sufficient to have a 2D map, so you also always should think about what's actually the best encoding for your data that you want to visualize. Yeah, with that I am at the end of my presentation part as well, so thank you all very much for your attention.
And if there are any questions? If there are any questions, yes, in the back.
You have a question about loading with the avalanche risks. I actually have two questions. One that comes to mind is that when you're zoomed out, the height map is generally more flat, right, than when you zoom in. But you kind of want to be conservative to show more risk than there possibly is when you're zoomed out. Are you dealing somehow with this?
Yes, so to repeat the question was whether, because there's a problem with the terrain model, that it actually gets smoothed or flatter the more you zoom out, and how I deal with this in the avalanche risk visualization. So yeah, that's a very good point. Actually, initially, one of my ideas was to have some sort of aggregate maximum aggregation basically for this terrain model, which I analyze so that I can always take the maximum slope steepness also in the tiles and encode it there in the pre-processing step. But I actually didn't do that in the end, and instead opted for just the ability to have different overlays at different levels, because I also did a user study with some recreationists and even mountain guides who talked a little bit about their tour planning process that they usually do. And they usually don't care so much from an overview perspective what the risk is on the individual slopes, but they look more on the actual, like just on the avalanche danger rating, where you can see, okay, in this region for the upcoming weekend or whatever, it's dark orange. So I wouldn't really consider going there anyway. And then only when you go to the more detailed tour planning, where you actually already then zoom in onto a certain area of interest, you're really interested in the localized avalanche risk. So to basically summarize the answer, no, I don't really deal with that in the visualization, but mainly because we found that actually it's not that necessary for the overview.
Yeah, and the second question is kind of opposite to this one. When you zoom too much in, you can be on a flat patch, but when you zoom out a little bit, you see that it's on a steep slope, right? So there should be a risk.
Yeah, that's what I also kind of was hinting at it with these Shure lines, that we want to have an area of influence basically around a high risk area that also goes below it, for example. And for that, for example, we would need to do some more sophisticated terrain analysis, because we don't actually just want to know the gradient at one point, but also what the terrain is around this one position, so that we can also take that influence, that area of influence into account. And at the moment, I'm also not doing that, because that would probably require some more pre-processing of actually classifying the terrain somehow. There are maps that do that basically try to classify, okay, what would be the total slope area for this one slope, and then what are the steepest parts here, and based on that they draw a map, which, Adam is just pulling that one up. They draw a static avalanche risk map, which takes this area of influence into account. And one idea would be to just maybe use that map as an additional input to to arrive at the avalanche risk there. But yeah, these are both very, very important considerations for that kind of visualization. So right now, basically, we release it with the disclaimer that when you use it, and you shouldn't just look at the immediate area of your tour, but also just expand a little bit. And that's also one of the reasons why we decided to color the whole terrain, because, for example, this website here, the sheet 1 blue that Alan's just showing, it also has a slope steepness overlay, but for the tours itself, it's just computes the avalanche risk for the tour track and displays it by encoding the tour track in different colors, but it doesn't really tell where the risk is coming from in this particular case. And so here you can see that the map is just a static steepness, and in the tour track you have different colors ranging from green to red, what the live risk based on the avalanche report would be. And so our goal was, okay, here it's very limited in terms of where is the risk coming from. So we actually want to expand on that and have it displayed for the whole terrain area around the tour as well.
I have a question. You mentioned the digital terrain model and the digital surface
Yes.
model. Can you maybe use these to calculate the snow layer thickness and incorporate it in the risk evaluation, or is it already included in the risk data you are getting from the server?
Mm-hmm. Yeah, so the question was whether we can use the digital terrain model and the digital surface model to estimate the snow depth. And the main problem here is these models are usually captured during summertime because they want to have the actual terrain information, not with the additional snow cover on top of it. So what we can, for example, use it for is to estimate where there are trees, because we can subtract the two models from each other and then have a bit of the tree coverage information there. I'm also currently not using that, but potentially could be using that because it also has an influence on the avalanche risk. But yeah, as you said, the snow cover information is kind of implicitly encoded in this avalanche report because they actually take samples of the snow and the snow conditions basically and the depth and so on, and factor that into their calculation for the danger rating.
Do you remember the website with the snow profiles?
The SLF thingy, right? White risk? What's the white risk?
An Austrian website.
The Austrian website, I don't know. I'm sorry.
You can take the next question.
Okay, are there any more questions or comments or discussion points? Did anyone get interested in rendering their own terrains now? Or did we just scare you away because it's so technical? I mean, like, for example, for the implementation I did, where I just used an existing framework, it was actually rather easy. The hard part in the beginning was to process the data in a way that it's understood by the rendering framework. And then, then it actually was super simple to spin up a first visualization.
So this is one of the snow measurements, and they take them, I don't know, in every region there are one or two on different expositions. And what they do is they cut through the snow and then they measure several things. One thing that they measure is the temperature, and then they also measure the stability of the snow. So the stability, the size of the snow, grains, and they put all of that into this thing. And yes, so this is just and from that they estimate the avalanche danger. Any other questions?
I have one, but it's a random technical one. So you mentioned that you developed the renderer like from the ground up, and I saw that you implemented it in C++ and you use Qt to visualize it on the map. And you also mentioned that you intend to maybe switch to Vulkan. And can you give us some insights on how do you achieve this on the web, or how do you use it, or do you transpile it to JavaScript somehow, or how do you use it?
Yes, so the renderer that the question was about technical background about the renderer that I wrote. And so yes, it's written in C++ and it compiles to Android native with OpenGL ES3 at the moment. Or it also compiles to WebAssembly, where it then wraps to WebGL2. I'm using Qt. So basically we have two GUIs. One of them is plain, so it's only the plain renderer. The idea is that at some point we might want to write an HTML user interface. The other user interface is QML based, which also uses QML's renderer, is also compiled to WebAssembly or Android native. And yes, I mean, it works. Basically WebAssembly. The other question was about a Vulkan implementation. This is something that we didn't do so far for several reasons. The first reason being that Vulkan is more complicated and I don't have experience in Vulkan. Second reason is that we wanted something that can target all of the platforms. So we, as a platform, we have the web, we have Android, we also want to support iOS, and OpenGL ES3/WebGL is like a common denominator. But in the future, we might very well switch to WebGPU/Vulkan. So I've heard yesterday or 2 days ago that there are header files which you can use in C++. And when you compile to WebAssembly, this would map to WebGPU. If you compile native, so that means Android, for instance, or also the desktop, then it would map to Vulkan. So in the future, it's very likely that we will use this, for instance, because we want to use compute shaders. And this is something that will be a question for the future, and at least at the beginning we would then have to support two rendering frameworks, one for OpenGL because still not all browsers support WebGPU, and the other one being WebGPU/Vulkan, and maybe we would also make some optimizations for Android because it's important for us to be energy efficient. Does that?
Yes, thank you.
Okay. Any other questions? Can be anything. All right.
Yeah, then we're done.
Then we are done, and thank you for coming. We were really scared that nobody will show up. And it's actually very